Okay, so let's do an example of how to trace genotypes through a pedigree using a autosomal dominant trait. So we have Fanconi anemia, and the dominant form of this phenotype is normal bone marrow. So if we set it up like the ones we're doing in class, we'd make our key up here, and we're going to trace the recessive trait. So normal bone marrow is the dominant trait. And having the anemia is going to be the recessive trait. So if we look at the people in our pedigree, we see that 4 people are afflicted with the anemia. So right off, we can put in their genotypes. The only way for them to have anemia is to have the 2 recessive alleles. Remember that 1 allele had to come from mom and 1 allele had to come from dad. Now to be normal, which means their square or circle isn't colored in, there's 2 possibilities for their genotype. They can be homozygous normal bone marrow, or they could be heterozygous for normal bone marrow. And so what we need to do is use the information we've been given to determine their genotypes. So I'm going to start with Anne and Michael on the right side of the pedigree. Carla has anemia. So each allele that she gets has to come from one of her parents. Now, one of the ways that I like to start out pedigrees and tracing genotypes is I use a pencil, number 1, so I can erase. But everybody that's not shaded in, I can go ahead and put their possible genotypes until I eliminate the ones that they are or are not. Because these are the 2 possibilities of their genotype. And we're going to try to figure out if we can determine if they only have 1 possibility. Okay, so if we go back to Carla, Carla had to get a little f from each of her parents. So 1 little f had to come from the mom, and 1 little f had to come from the dad. And the only way that's going to be possible if both Anne and Michael are heterozygous for the trait. So that's the only possibility. Okay, if we go up to George and Arlene, they have 2 children afflicted with anemia. Again, if we look at Wilma, she had to get 1 little f from mom and 1 little f from dad. So that only possibility for dad would be that he has the heterozygous genotype. And if you wanted to check that and make sure, you could do the Punnett square of big F crossed with big F little f. And if you did that Punnett square, you would see that you would have 2 possibilities being big F, and 2 possibilities being big F, little f. So it's impossible for them to have a child with 2 little f's. So he cannot be big F. Okay? So then if we look at their children, they have 4 children, and we try to figure out Sam's genotype. Again, the only allele that mom is donating is a little f. So all of her children are going to have at least 1 little f in their genotype. So that means that Sam isn't big F. Okay? Now if we go to Sandra and Tom and look at their 2 children, they have 2 boys, we can figure out their genotype. Because Tom can only donate a little f, that means the children have to have at least 1 little f in their genotype. Now, if we look at Sandra, we don't have her parents to look at to see if they had the trait, and none of her children have the trait. So we don't know whether she's big F, or big F, little f. So we have to put both genotypes in for her. Then if we go on down to Alan and Tina, we figured out Alan's genotype, but Tina, we don't know anything about her parents, and they haven't had a child that's afflicted with anemia yet. So we have to leave both Tina and Christopher as big F, little f, big F, because we don't know their possibilities. And that's how you trace genotypes back through an autosomal dominant pedigree.